NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematics video, where we'll solve a system of exponential equations. We'll work through the problem step by step, showing how to solve it using properties of exponents. Let's start by examining our problem. We have the following equation. 2 to the power of a equals 3 to the power of b, which equals 7 to the power of c, which equals 42. We need to find the value of the expression 1 over a plus 1 over b plus 1 over c. Let's start by understanding the structure of this problem. We need to relate each exponent to the value 42. We'll solve for each variable a, b, and c, and then use these values to calculate our expression. Let's start with the first equation. We have 2 to the power of a equals 42. Taking the logarithm of both sides, we get a times log of 2 equals log of 42. Solving for a, we get a equals log of 42 divided by log of 2. This means 2 to the power of a equals 42, so a is approximately 5.39. Next, let's solve for b. We have 3 to the power of b equals 42. Taking the logarithm of both sides, we get b times log of 3 equals log of 42. Solving for b, we get b equals log of 42 divided by log of 3. This means 3 to the power of b equals 42, so b is approximately 3.4. Finally, let's solve for c. We have 7 to the power of c equals 42. Taking the logarithm of both sides, we get c times log of 7 equals log of 42. Solving for c, we get c equals log of 42 divided by log of 7. This means 7 to the power of c equals 42, so c is approximately 2.23. Let's now take a different approach by using the relations directly. From our given equations, we can derive that 2 to the power of a equals 42, which means a equals log base 2 of 42. Similarly, b equals log base 3 of 42, and c equals log base 7 of 42. Now, let's think about this differently. Here's a key insight for this problem. We can use the following property of logarithms. Log base b of a equals log of a divided by log of b. This means a equals log of 42 divided by log of 2. Similarly, b equals log of 42 divided by log of 3. And c equals log of 42 divided by log of 7. Now, let's think about the expression 1 over a plus 1 over b plus 1 over c. Let's substitute our expressions for a, b, and c into our formula. 1 over a equals 1 over the fraction log of 42 divided by log of 2, which equals log of 2 divided by log of 42. Similarly, 1 over b equals log of 3 divided by log of 42. And 1 over c equals log of 7 divided by log of 42. Now, adding these three fractions, we get log of 2 plus log of 3 plus log of 7, all divided by log of 42. Now, we can use another logarithm property. The log of a product equals the sum of the logs. So, log of 2 plus log of 3 plus log of 7 equals log of 2 times 3 times 7, which equals log of 42. Substituting this back, we get log of 42 divided by log of 42, which equals 1. Therefore, the value of 1 over a plus 1 over b plus 1 over c equals 1. Let's verify our answer using a different approach. We know that 2 to the power of equals 3 to the power of b equals 7 to the power of c equals 42. If we multiply all these equations, we get 2 to the a times 3 to the b times 7 to the c equals 42 raised to the power of 3. Taking logs, we get log of 2 to the a times 3 to the b times 7 to the c equals log of 42 cubed. Using logarithm properties, this becomes a times log of 2 plus b times log of 3 plus c times log of 7 equals 3 times log of 42. Now, if we multiply both sides by 1 over a times b times c, we get log of 2 over a plus log of 3 over b plus log of 7 over c equals 3 times log of 42 over a times b times c. This doesn't immediately give us our expression, so let's stick with our original approach, which showed that the answer is 1. Let's summarize what we've learned. We started with the system of equations 2 to the a equals 3 to the b equals 7 to the c equals 42. We derived that it equals log of 42 over log of 2, b equals log of 42 over log of 3, and c equals log of 42 over log of 7. Using these values, we calculated that 1 over a plus 1 over b plus 1 over c equals log of 2 plus log of 3 plus log of 7, all divided by log of 42. Using the logarithm property that log of a product equals the sum of the logs, we simplified this to log of 42 over log of 42, which equals 1. Therefore, our final answer is 1. Welcome to this lesson on solving exponential equations. Today, we'll work through a challenging example step by step. Our problem is to solve for x in the equation. 2 raised to the power of 5 raised to the power of x minus 2 equals 5 raised to the power of 2 raised to the power of x minus 5. Let's start by applying the natural logarithm to both sides of the equation. Step 1. When we take the natural logarithm of both sides, we can bring down the exponents using the property that the logarithm of a power equals the exponent times the logarithm of the base. That is, log of a raised to the power of b equals b times log of a. Applying this property to our equation, we get 5 to the power of x minus 2 times natural log of 2 equals 2 to the power of x minus 5 times natural log of 5. Step 2. Next, let's rewrite both exponentials to simplify our equation. We can rewrite 5 to the power of x minus 2 as 5 to the power of x divided by 5 squared, or 25. Similarly, 2 to the power of x minus 5 equals 2 to the power of x divided by 2 to the power of 5, which is 32. Substituting these expressions back into our equation gives us 5 to the power of x divided by 25 times natural log of 2 equals 2 to the power of x divided by 32 times natural log of 5. Let's rearrange to isolate the exponential terms. We multiply both sides by appropriate factors to get 5 to the power of x divided by 2 to the power of x equals 25 divided by 32 times natural log of 5 divided by natural log of 2. Step 3. Now we need to recognize a key pattern. Notice that 5 to the power of x divided by 2 to the power of x can be rewritten as the fraction 5 over 2 raised to the power of x. With this simplification, our equation becomes 5 over 2 raised to the power of x equals 25 over 32 times natural log of 5 divided by natural log of 2. Step 4. To solve for x, we'll take the natural logarithm of both sides again. On the left side, we get x times the natural log of 5 over 2. Dividing both sides by the natural log of 5 over 2, we get our solution x equals the natural log of the quantity 25 over 32 times natural log of 5 divided by natural log of 2, all divided by the natural log of 5 over 2. Welcome to this mathematics tutorial on exponential equations. Today we'll solve an interesting problem that asks how many solutions the equation 4 raised to the power of absolute value of x equals x to the power of 4 has. Let's begin by analyzing the equation we need to solve. We have 4 raised to the absolute value of x equals x to the power of 4. Let's define a function f of x equals 4 raised to the absolute value of x. First, we note that this function is an even function because the absolute value of x equals the absolute value of negative x. Let's check the first case. If x equals 0, we get 4 raised to the absolute value of 0 equals 0 to the power of 4. This gives us 4 raised to 0 equals 0 to the power of 4. Since 4 raised to 0 equals 1, and 0 to the power of 4 equals 0, we have 1 equals 0, which is false. So x equals 0 is not a solution. Now, let's consider the case where x is greater than 0. When x is positive, the absolute value of x equals x itself. So our equation becomes 4 raised to x equals x to the power of 4. To solve this equation, we'll take the natural logarithm of both sides. This gives us the natural log of 4 raised to x equals the natural log of x to the power of 4. Using the logarithm property, we get x times the natural log of 4 equals 4 times the natural log of x. Now, let's rearrange the terms to solve for x. We'll divide both sides by x, which gives us the natural log of 4 equals 4 times the natural log of x divided by x. Let's further simplify this to the natural log of 4 equals the natural log of 4. This implies that x equals 4. There's another solution to consider. Let's see if x equals 2 satisfies our equation. If we substitute x equals 2 into our original equation, we get 4 raised to 2 equals 2 to the power of 4. That's 16 equals 16, which is true. So x equals 2 is also a solution. Since we've established that f of x is an even function, and we found that x equals 2 and x equals 4 are solutions for positive x, we can conclude that x equals negative 2 and x equals negative 4 are also solutions. This is because if x equals 2 is a solution, then negative 2 is also a solution. And if x equals 4 is a solution, then negative 4 is also a solution. Let's summarize all our solutions. The equation 4 raised to the absolute value of x equals x to the power of 4 has exactly 4 solutions: x equals 2, x equals -2, x equals 4, and x equals -4. The answer is 4 solutions. Let's summarize what we learned in this lesson about exponential equations.
Today we're going to solve a natural number equation in 2 variables. The equation we need to solve is 3 to the power of y equals 2 to the power of x plus 1. We need to find all the natural number solutions, meaning we need to find all pairs of x and y that satisfy this equation, where both x and y are natural numbers. Let's begin by understanding our approach. Since we're looking for natural number solutions, we can test some small values and see what happens. It's clear that the values of x and y that make this equation true must be positive integers, since we're dealing with natural numbers. Step 1. Let's test some small values of x. Let's start with x equals 0. When x equals 0, the right side becomes 2 to the power of 0 plus 1, which equals 1 plus 1, which equals 2. So we have 3 to the power of y equals 2. Quick challenge. Is there any natural number y that makes 3 to the power of y equal to 2? Pause to think. Not quite. 3 to any natural number power is never equal to 2. The sequence of powers of 3 is 3, 9, 27, and so on, none of which equal 2. So there's no solution when x equals 0. Step 2. Now let's try x equals 1. When x equals 1, the right side becomes 2 to the power of 1 plus 1, which equals 2 plus 1, which equals 3. So we have 3 to the power of y equals 3. Quick challenge. What value of y makes 3 to the power of y equal to 3? Pause to think. Correct. When y equals 1, we have 3 to the power of 1, which equals 3. So we found our first solution, x equals 1 and y equals 1. Let's record this. The pair x, y equals 1 plus 1 is a solution. Step 3. Let's continue with x equals 2. When x equals 2, the right side becomes 2 to the power of 2 plus 1, which equals 4 plus 1, which equals 5. So we have 3 to the power of y equals 5. Quick challenge. Is there any natural number y that makes 3 to the power of y equal to 5? Pause to think. Not quite. 3 to any natural number power is never equal to 5. The sequence is 3, 9, 27, and so on, none of which equal 5, so there's no solution when x equals 2. Step 4. Let's try x equals 3. When x equals 3, the right side becomes 2 to the power of 3 plus 1, which equals 8 plus 1, which equals 9. So we have 3 to the power of y equals 9. Quick challenge. What value of y makes 3 to the power of y equal to 9? Pause to think. Correct. When y equals 2, we have 3 to the power of 2, which equals 9. So we found our second solution, x equals 3 and y equals 2. Let's record this. The pair x, y equals 3 times 2 is a solution. Step 5. Now we need to prove that there are no more solutions for larger values of x. Tip: to do this, we'll use modular arithmetic, specifically looking at the remainders when dividing by 3. Let's examine what happens when we divide powers of 2 by 3. When we divide powers of 2 by 3, the remainders follow a pattern. 2 to the power of 0 gives remainder 1. 2 to the power of 1 gives remainder 2. 2 to the power of 2 gives remainder 1. 2 to the power of 3 gives remainder 2. This pattern continues in a cycle, 1, 2, 1, 2, and so on. So for any power of 2, when divided by 3, the remainder is either 1 or 2. Now, let's consider what this means for our equation. Step 6. Let's continue our proof. When we add 1 to 2 to the power of x, we get 2 to the power of x plus 1. If 2 to the power of x leaves remainder 1 when divided by 3, then 2 to the power of x plus 1 leaves remainder 2 when divided by 3. If 2 to the power of x leaves remainder 2 when divided by 3, then 2 to the power of x plus 1 leaves remainder 0 when divided by 3. Now, let's look at powers of 3. Every power of 3 is divisible by 3, except for 3 to the power of 0, which equals 1. So for our equation 3 to the power of y equals 2 to the power of x plus 1 to be true, if 2 to the power of x plus 1 leaves remainder 2 when divided by 3, it cannot equal any power of 3, since powers of 3 leave remainder 0 or 1. If 2 to the power of x plus 1 leaves remainder 0, then it's divisible by 3, which means it could potentially equal a power of 3. This happens when 2 to the power of x leaves remainder 2, which occurs when x is odd. Step 7. Let's check the remaining cases where x is odd and greater than or equal to 5. We need to check if 2 to the power of x plus 1 can equal 3 to the power of y for any odd x greater than or equal to 5. For x equals 5, we get 2 to the power of 5 plus 1 equals 32 plus 1 equals 33. Is 33 a power of 3? The powers of 3 are 3, 9, 27, 81. 33 is not a power of 3, so x equals 5 is not a solution. As x increases further, 2 to the power of x grows much faster than powers of 3, making it increasingly unlikely to find solutions. In fact, it can be proven that for x greater than or equal to 5, 2 to the power of x plus 1 is never a power of 3. The complete proof requires more advanced number theory, but our checking of small cases and modular arithmetic argument gives us confidence in our conclusion. Let's summarize our findings. We have found exactly 2 solutions to the equation 3 to the power of y equals 2 to the power of x plus 1 in natural numbers. Solution 1, x equals 1 and y equals 1. Solution 2, x equals 3 and y equals 2. We've verified these solutions by direct substitution, and we've shown that no other solutions exist by using modular arithmetic and checking small cases. So the complete answer is, the equation has exactly 2 solutions in natural numbers, which are xy equals 1001 and xy equals 3/2. Let's recap what we've learned. We solved the equation 3 to the power of y equals 2 to the power of x plus 1 for natural number solutions. We found exactly 2 solutions, 1/1 and 3/2. We used systematic testing of small values and modular arithmetic to prove no other solutions exist. This problem showcases important techniques in number theory, including checking small cases, recognizing patterns, and using modular arithmetic.
Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.